Hi, I'm Julie Callahan, and I am coming to you from my family room where I have worked since March. So, welcome to my family room. I work with Telescope Array, which is a cosmic ray research program at the University of Utah in the Department of Physics and Astronomy. I am the project coordinator for an outreach program called Aspire. We provide lessons and labs in an online forum for K through 12 teachers and students, and we provide hands-on demos and activities both in person for classroom presentations and like star parties, steam fests. uh, Pretty much anybody who asks me to come do demos, if my schedule's open, I try and show up and do it because demos are fun. So today I will be giving you a little presentation about cosmic ray research at the University of Utah. This is one of the types of outreach that I do, is bringing this kind of information to high school classes and informing high school students about opportunities in research. Whether that's cosmic rays, that would be great, but just realizing that there are research opportunities at a university like ours is great. And then we'll do some hands-on activities, which is always the fun part for me. All right, we'll start with this PowerPoint presentation first. You'll notice along this very desolate stretch, or the loneliest road in America, that there are these odd-looking rusty things on the side of the road. And some people say they look a little like hospital beds, but they do have this solar panel which confuses everyone. What in fact it is part of our array, of the telescope array. These are scintillator detectors that are spread out on a grid. We have hundreds of these that all work together to measure some of the highest energy particles observed anywhere. We have another part of our experiment. This is the fluorescence telescope station. We have 3 of these. This is located at the Black Rock Mesa, and this one is fairly large. You can see this area is flat. We have very clear skies. These are all important factors for studying cosmic rays the way that we do. This is the middle drum fluorescence detector. These detectors are from a previous experiment. We've upgraded the software and some of the electronics that operate it, but functionally it's mostly the same. These mirrors are 2 meters across. They gather light at night when there is no moon and focus it onto an array of photomultiplier tubes. Well, what is a cosmic ray? They were first discovered in 1912 by Victor Hess. He had just learned about this radiation. It was very interesting, but he proposed that it was mostly Earth originated. So he wanted to go up higher into the atmosphere to see if he could get away from it. This is an electroscope, and which you would charge up this plate here, and down here are 2 gold leaves, and when they become charged, negatively charged with electrons, they repel against each other. So as you have a charged particle pass through these 2 leaves would come together. And as he went higher and higher in elevation, what he found is that radiation did not decrease. In fact, it increased. And he realized that space is full of this radiation, and so he dubbed them cosmic rays. And he won the Nobel Prize for this in the 1930s. Okay, so this is the flux chart, the famous flux chart. And so what we find is that this is a log. At the lowest energies down here, things that might come from the sun or locally sourced, we have a high amount of particles that we see or observe. Some people use the comparison that you'll get 2 particles through your head every second, or 1 particle through your hand. They're very common, and as we increase in energy, we see there's a dramatic fall off. So at some point, like 10 to the 11th, you expect to see 1 particle per square meter per second. And at the highest energies, we would expect to see 1 particle per cubic kilometer per century. So cosmic rays are studied by telescope array in the region of 10 to the 17th and above. So these are extremely rare particles. We don't see them much. So what we need is a very large apparatus, a very large detector. So one of the things that we ask ourselves is, where do these particles come from? We don't know. We have some guesses, but we still really don't know. And there are some additional problems. At energies above 10 to the 18th electron volts, cosmic rays begin to interact with the cosmic microwave background radiation. And so at these energies, they can interact with photons. They start to lose some of their energy as they travel through space. So by the time they arrive at Earth's atmosphere where we can observe them, if they have traveled a certain distance, they would lose their energies. So when we look at these particles with these extremely enormously high energies, and we look back in the sky at what's there within about 150 million light years, it's empty. There's not really anything there in the sky that would explain the energies at which we're seeing. So how do we detect these ultra-high energy cosmic rays? We think these cosmic rays are mostly protons. They're charged particles. And as they travel through space at these enormous energies, they are mostly unimpeded until they reach our upper atmosphere. And when that happens, we'll see a particle enter our atmosphere. Suddenly, there's a pretty thick gas that it has to permeate. And it doesn't get too far before it'll probably collide with nitrogen. And there's so much energy there that this nitrogen just gets broken into all of its subcomponents. And those in turn retain a huge amount of energy and break apart and collide with nearby neighbors. And so the ending result is something like this, where you develop, hundreds and thousands and millions of particles, and until we get just an enormous amount of snowball effect and particles that develop over this distance. As this is happening, the gas in the atmosphere is getting nudged and excited by all these charged particles. And as that occurs, there's some ultraviolet light that's given off through this event. So we call this event an extensive air shower. And so our technique uses 2 methods where we image the light, the ultraviolet light generated by this event, and then our ground array samples at the ground level particles that are generated by this extensive air shower event. Okay, here comes our particle. If you can see that, it's kind of hard to see. Boom, it collides with nitrogen. And we see the front as it's developing. And you can see that it hits a few of these detectors. The name air fluorescence is the name that's given to this technique where we observe ultraviolet emissions in the atmosphere. It was this experiment, the Fly's Eye, from 1978 to 1993, that operated at the Dugway Army Proving Ground, was able to observe these particles using this technique. This particle is the world's highest energy particle that was observed in 1991 at Fly's Eye. So the University of Utah holds the world's record for the highest energy particle ever observed anywhere. This is a map that shows the footprint. Each one of these blue dots represents one of those rusty scintillator detector boxes. This whole little spot right here, that's our entire experiment. It's pretty large. So you can see that we have a very large footprint. This is a representation of an event that occurred on October 26th in 2008. So this is Middle Drum. This is Long Ridge. You can see the same event. This is Black Rock Mesa. And then this is our surface detector. This is the footprint of that front of particles that we saw. About 2 years ago, we had collected around 80 events. Now we just look at the northern hemisphere here, and it's kind of isotropic until you get to a certain point. you start to see a clustering. If you look at each one of these squares in the sky, and you look at how many of these events are in these squares, well, we start to see this really interesting feature right here. So with this information, we needed to get more data to get a better idea of what might be causing these particles. So we've actually expanded. So it's an enormous amount of area, and we can collect data 4 times as quickly as we did before this expansion. Of our detector in Utah, and this is the borders for the state of Rhode Island. We take approximately the same amount of square mileage. Our footprint is about the same. So as we collect this data, we would expect to see more interesting features. As we run these through simulations, we can see tighter spot here, or there might be able to be a double spot. We're still not sure. And so we'll be able to understand this better as we collect more data. Okay, so we're here in some low light conditions to demonstrate the plasma ball, which is very popular with scientists of all ages. So no matter where I take this demo, people love it. So there's a plasma inside of this globe, or a thin gas, and this thing in the center is a high voltage capacitor, which is releasing a large amount of energy that when it travels through this gas, it has an optical effect called a corona discharge effect. So it kind of is isotropic in all directions where these lines are seeking out some sort of conductor. It's just going to the air. But if I put something in close, like my hand, which is full of water, it's a low voltage conductor, and it really likes that. So of course it's going to deposit all that energy into my flesh. So there's energy coming off of this all around that we can't necessarily see because there's some ultraviolet that happens there. So if I take something like a light bulb, a fluorescent light bulb, and I move it closer to this object, I don't know if you can see that, it's starting to turn off. Maybe I should move so you can see with the dark background. You see it's starting to glow until it turns all the way on. So the gas inside the fluorescent bulb is being excited by the energy coming off of this plasma sphere, and then it goes through the fluorescence process where the gas gets excited, it releases a photon in the ultraviolet, which encounters the white phosphor coating and converts that into from an ultraviolet photon into a visible light wavelength that we can see with our eyes. All right, never gets old, never gets old. All right, so we talked about the plasma globe and how we can use it to observe the process of fluorescence, where we can take invisible light and excite a gas like the one in a fluorescent light bulb and cause it to light up without a direct energy source. So another demo that I use to describe how fluorescence works, and this is always very impressive because these things are toxic dishes. This is called Vaseline glass, and it was really popular in the Depression, pre-World War II. And you can see this one's kind of yellow. This one's a little bit green. And these have both been created using uranium crystals. So what people could do then during that time is when it became exposed to ultraviolet light, it would fluoresce. I don't know if you can kind of see that. Let me turn off this other light. Turn it down. This will be much more impressive. There we go. So you can see that this is fluorescing when it encounters ultraviolet light. Oh, that's really interesting too. What you can see in the video that I can't see in person is there's this kind of red bleed that's happening around here too. So there's something funky going on with my camera sensor. It's picking up frequencies that are being emitted that my eye can't see, but that the sensor can see. That's interesting. Okay, this is another one that's green. You can see it fluoresces, and we're getting that same kind of interesting little light bleed off the side. Oh, that's really cool. Must be infrared or something else. Maybe it's just the color it's converting to. So these can be a little tricky to find. Sometimes you can find them in thrift stores, but it's not always a guaranteed find. They can be expensive. But one thing you can buy are marbles that have been created for this purpose, for educational outreach purposes. And these marbles also fluoresce when put under ultraviolet light. Okay, so this is an activity that I designed over a couple of years and had many different iterations until I finally came up with a design that I liked. So this is one that I do quite a bit. It's a basic Wilson's cloud chamber. So you can see here I have a block of dry ice. It's pretty flat. It's all one piece. That's important for the success of this project. I've had this machined. It's aluminum, 1/4 inch aluminum, and it's got like a little moat that's been carved in there. And you'll see why that is in a moment. But it's also been anodized, and that's simply for the black color and to make this more durable. You could do something similar to this with like an aluminum Dutch oven that has like a black coating on it. That might work. You might be able to hit a thrift store and make one of these on your own. And you don't have to spend as much money or time designing it like I did. Okay, so what we're gonna do is put this on our block of ice. But you can see right away I have some issues going on here. It's slipping around, it's going all over the place. So I need to get something that'll cause a little bit of friction for that. Oh, here it is. So I have a tiny little piece of paper towel. So I just put that down, and it adds enough friction and support that I'm no longer going to get the sliding. Sometimes you get a really cool acoustic effect as well. Didn't seem to happen here this time. Okay, so this is cast acrylic tubing. It works really well for the position that we're in. And this is going to be the walls of our chamber. And we'll be able to view inside the chamber using this. Now there are a few different radiation sources that you can use inside of a cloud chamber to actually observe subatomic particles. You don't actually see the particle, but you see an ionizing track where that particle was. So I have these fancy sources that I got from a company called Canberra. I don't know that they're making them anymore, but and they're not cheap. But if you wanted to do this and make your own, it is entirely possible if you are near an Army-Navy store. So this is, I have it all plasticized because it's actually pretty toxic. You don't want to handle this too much. After I get done here, I'm just going to go wash my hands really well. So these are camping mantles, and these are not the Coleman brand. Coleman brand will not work. This is Tech Sport, and it's just kind of a cheap knockoff of that. And on the back here, it actually says hydroxides and nitrates of thorium, cerium, and aluminum, magnesium, and calcium. So the thorium is the important one that we want to look for there. And all you have to do is take a tiny little thread off of that mantle. You can see that tiny little nubbin of thread that I pulled out. And that is going to be hot enough to see some really great tracks. But for now, I think we're going to try and use our cloud chamber needle source. So these are activated lead. So they've been exposed to polonium. PB210, I think was the write-up on it. And I have a vial. And what's on there that you can kind of see is a sewing needle. And it's just the very, very tip of the needle that's been exposed. So I'll put that down in here. But we won't be able to see anything until we get some sort of vapor that happens in there. And our atmosphere is not appropriate for this kind of vapor. So we are going to induce a different kind of an atmosphere within this chamber using, it's kind of hard to see, this is the 91% isopropyl alcohol. Got it pre-COVID, so it's, you can use some other really high proof alcohols if you can't actually find this one. But if you use the 70% alcohol, it won't work. There's too much water in it. And water will actually freeze with this dry ice, whereas alcohol will just super condense and super cool. Okay, so what I'm pouring this on right here is the lid. There's a kitchen sponge, and I am just saturating that until it soaks the whole thing up. There's it's starting to drip a little bit off the sides here. I don't know if you can see that. So it'll evaporate quite quickly. So as soon as we're ready, we'll throw this on. And now we're going to have precipitation that occurs within this chamber. One thing I also like to do is I like to pour a little bit of alcohol along the bottom here just to kind of seal off this area so that we don't get any air leaks that go into this space. Okay. So it's going to take maybe 5 minutes, maybe a little longer. It depends on the temperature, the barometric pressure and the humidity, and how much alcohol is precipitating in there. But fairly soon, what we'll be able to see is these little tracks. They look like fireworks, but they look like if fireworks were made out of spider webs, which is, it's really beautiful. And those tracks are actually the molecules of alcohol that are condensing around the charged particle as it passes through. So our cloud chamber emitter is creating, it's emitting alpha particles. And an alpha particle is 2 protons, 2 neutrons, and so it's positively charged, relatively heavy. It doesn't go very far before it turns into regular helium, and so, or, collides and turns into something else. If it hits the outside of this plastic, it's just not going anywhere. So alpha particles are very low interacting. But like those dishes that we saw with the fluorescence demonstration, you don't want to drink or eat off of dinnerware that has uranium in the glazes or in the glassware. There's a reason they don't sell that stuff anymore. It's because it's not healthy to ingest. And there are actually some particles that come off of this. It's about 97% alpha particles and about 3% beta. Okay, I'm actually seeing tracks in here already. So I'm going to get my phone and we'll do a close-up with my phone. And I have a special light. I'll pull that over so we can see them a little bit better. All right, here is our cloud chamber needle source, and you can see those condensation trails. So it's not an actual particle that you see, but it's a track of ionized particles that condense around it. You can see it's getting colder, we're getting more vapor, we're starting to see more particles. Every once in a while, you'll see a particle that comes from some source that's obviously not the eye of that needle. And that is a particle of unknown origin. We would call that a cosmic ray. I don't know if it's from space. It's probably, since we're in the basement, from concrete or, potassium there, or it could be contamination in here. Who knows where these things come from. So, but this is what? Oh, did you see that cosmic ray down towards the bottom? There's another one. So we see a couple of good ones. I haven't had my home tested for radon. Maybe I should. Okay, there was another good one. I just saw 3 cosmic rays. All right, the straighter the path, those are alpha particles. If you see one that kind of corkscrews, they're not as frequent, but you see one that spirals or corkscrews, that's most likely a beta particle. And if you see one that seems like it's forking off of an already existing particle, that's likely muon decay. All right, so hopefully you've enjoyed this. You can go home and make one of these and watch all of the radiation and entertain yourself. Another fun project you can do with dry ice, since it's the holiday season coming up, is you can get tonic water, and which fluoresces under ultraviolet light. If you have a UV light, you can throw some dish soap in a bowl with tonic water and some dry ice. You put a black light in that and it's gonna foam up and make awesome bubbles. Really great Halloween decoration. So both cool for science and for decor. So I just wanted to say a special thank you for spending some time and watching my video. Hopefully you had fun or learned something interesting or new. Research is exciting. It's something you can get involved in as an undergraduate in our department, which is exciting. And part of that research can also be in helping to provide outreach. This is something all NSF grant-funded programs need to provide, and helping them to do that and report on that is so helpful for your professors if that's something you're involved in. There's also student groups like SPS and WAMPA. They do a lot of presentations, and there's probably some really cool opportunities with the current quarantine situation to maybe do some video Zoom type demo presentations. Could be quite exciting. All right, thanks. Have a good weekend.